Okay, then, welcome everyone to the colloquium of the Physics Institute of the UNAM in Cuernavaca. Our guest today is Jiri Vanicek from the École Polytechnique Fédérale de Lausanne in the Swiss. Let me say some very few words about the vitae of Jiri. So he did his PhD in theoretical physics at the University of Harvard. And then he realized a postdoc at the University of California in Berkeley. And afterwards, he became a member of the Institute of Advanced Study at Princeton. And since 2007, he is a professor at the EPFL in Swiss. And Jiri's research focuses on theoretical molecular quantum dynamics and bioinformatics. So, Jiri, thank you very much for accepting my invitation to participate in our colloquium. It's a pleasure for us, and also for working late night. I think it's 8 p.m. in the Swiss, and
It's okay. This is my most productive time.
Okay, we're looking forward to your talk, Jiri.
All right. So thank you very much. Thank you, Thomas, and thank you, Thomas, for the invitation. It is nice to be back to Cuernavaca, at least virtually, although I hope to come back again soon after the coronavirus is over. It has been always nice to come back to workshops organized by Thomas Seligman. I miss that I'm not there in person, but I guess nobody is today. So thank you for the invitation, and I would like to tell you about recent developments in our group in the area of on-the-fly ab initio semiclassical dynamics, and specifically how this method can be used to compute vibrationally resolved electronic spectra. So this has been a work in progress over the last around 5 years, and various students and postdocs have contributed. I would like to highlight Tomislav Begusic, who has made the most recent progress in the area, and Marius Verle, who got us started with this approach. But it is also Roya, Solène, Aurélien, Julien, and Miroslav who played an important role. Okay, so here is an outline of my talk. So first, I would like to define for you what I mean by on-the-fly ab initio semiclassical dynamics. And then I'll tell you about the simple thawed Gaussian approximation for quantum dynamics. And I'll make a quick review of time-dependent approach to spectroscopy. And so finally, I can show you several examples of absorption and emission spectra. And here, the 3 items which are underlined are the exciting, I think, at least for me, the new developments, that because these calculations are quite expensive, we need ab initio electronic structure. So any way to accelerate it is good. So one approach is a single-Hessian approximation. And then I will talk about generalization of the Gaussian approximation to describe electronically forbidden spectra. And there is a famous example of benzene, which I will show you. And then finally, how we can describe spectra at finite temperature without dealing with the density operator. So I'll show you a trick which allows you to use wave function picture to describe finite temperature. And at the very end, I will just advertise some more fancy applications with time-resolved and 2-dimensional spectra. Okay, so what is on-the-fly ab initio semiclassical dynamics? So first, let me try to motivate what is the main goal of doing quantum ab initio simulations of molecules. There are these fancy experiments which are ultra-fast, time-resolved experiments with bump and probe laser pulses, in which a bump pulse excites the molecule to the excited potential energy surface. The molecule feels this potential energy, moves there, and then the probe pulse sends it back to the ground state. And then the experimentalists measure a spectrum which is both resolved as a function of energy and as a function of time delay between the bump and probe pulses. So it provides a lot of information, but still, if you just look at the spectrum, it may be difficult to understand the dynamics. So the main goal is to understand what is the microscopic dynamics underlying chemical reactions and physical processes induced by the interaction of molecules with light. Okay, and one can say it even in more vulgar terms. I would say, can one make a quantum molecular movie? So I don't want to be fashionable or something, or it's maybe a cliche, but I think it is interesting. With time-resolved spectroscopy, people, also experimentalists, try to capture the molecules as they evolve in real time and with femtosecond resolution. But I feel that it is still a little bit inverse problem. So I'm always impressed when people measure a spectrum, for example, like this over here. It's relatively simple, it has few peaks, and then they can write a detailed story about which atoms moves where and which electron moves where and so on. And for me, it's complete magic. I think it is, in some sense, an inverse problem, because if I give you a spectrum, can you really tell me everything about dynamics? I'm not so sure, right? So there's this famous question by a mathematician from the 60s, Markacha, can one hear the shape of a drum? I think most of the people in the audience have also heard about this, but in case not, imagine that you have a drum, you don't know, it doesn't have to be round, you hit it with your hand and you just listen to the vibrations. Is it possible to determine what is the shape just by hearing the frequencies? So there is also this famous picture that people found, isospectral drums, which have exactly the same spectrum, but in real life spectroscopy, you don't have only the frequencies, you have also intensities. And then perhaps it is actually a well-defined problem once you include the intensities. But I don't want to be too philosophical. I just want to say from the theory point of view, the problem is well-defined, but it is difficult, right? All we need to do is to solve many-dimensional time-dependent Schrödinger equation. So we know everything about the dynamics first, and only then we compute the experimental observables, such as spectra or something else. And again, there is this famous quote by Paul Dirac already from 1929, which is perhaps slightly controversial too. So the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known, and the difficulty lies only in the fact that application of these laws leads to equations that are too complex to be solved. But it's, in some sense, it is good, because now it is almost 100 years after this statement, and still it keeps us in business, that we have to work hard to be able to solve this equation. So let me describe a little bit what is the problem. So I would say that the state of the art is, for example, is quantum dynamics with model potentials. I stopped the movie for a second. So you can do exact quantum dynamics, solving the time-dependent Schrödinger equation for nuclei, but it's in model potentials and relatively few dimensional. This one is a 4-dimensional projected to 2 dimensions. So you may have seen that there was a pump pulse which excited the molecule to the second excited state. Then due to non-adiabatic couplings, it moved to the first excited state. And then finally, the probe pulse sends the molecule back to the ground state. It's a very simple system, but you see that the dynamics is already quite complicated even there. And there is no way to do it as rigorously, for example, in 30 dimensions, which is 10 atoms is already 30 dimensional. So another approach is so-called ab initio classical dynamics. So this one is the same. This is the same experiment. And now we visualize the molecule with balls and sticks, and you're just solving the Newton's equation for the atoms. It is still the state of the art, because the forces are computed by solving the time-independent Schrödinger equation for electrons. So this is really ab initio molecular dynamics, but it doesn't tell you anything about nuclear quantum effects and interference, tunneling, and so on. So what we are trying to do is to take the best of the two approaches and do ab initio semiclassical dynamics, where you represent the nuclear wave function or atomic wave function as a sum of over trajectories. So each trajectory here corresponds to one replica of the pyrazine molecule, and it actually gives you much more intuition about what happens in the molecule. For example, you see that the hydrogens are much more spread than the carbons or nitrogens, And the reason is because hydrogens, of course, have much bigger de Broglie wavelengths. Second, you can visualize in which electronic state the molecule is moving. Here we visualize it by the color of the hydrogens. And finally, of course, you can describe interference because each trajectory has a phase factor associated to it. Okay, so there are various methods that do this. I just want to point out, because several people in the audience are experts in quantum fidelity, that specifically this method was a generalization of the dephasing representation to multiple electronic states. But it's not important for the rest of the talk. Okay, so when you say on-the-fly ab initio semiclassical dynamics or first principle semiclassical dynamics, it looks interesting in theory or promising, because on-the-fly ab initio means that you evaluate the expensive electronic structure only where you need it along the trajectory. Right? You don't need to compute potential energy surface in 100 dimensions, which you couldn't even store on a computer. So you only compute it along the trajectories. And because you do semiclassical dynamics, you include at least interference and some other most important quantum effects. But it's very difficult in practice, because one of the first really rigorous semiclassical ab initio calculation was absorption spectrum of formaldehyde, which required 6,000 trajectories for convergence. And this is very expensive if you need to solve Schrödinger equation for electrons along each trajectory. So it's not simple. And unfortunately, it requires various compromises. So you cannot do it with the most sophisticated semiclassical method, but it's okay to make a compromise. And I say it's okay because many quote unquote practical spectra calculations, which are included in various software packages, still rely on much more simple global harmonic approximations, or even worse. Okay. And on the other hand, it is still necessary to make these compromises, because you cannot afford ab initio calculations with 100,000 trajectories, especially because you need not only force, but also the Hessian of the potential energy surface. So this is in contrast to just running classical trajectories. Semi-classical methods need also the Hessian of the energy. And one such a compromise is provided by a thawed Gaussian approximation. This is a very old and simple approach in which the wave function is approximated simply by a Gaussian, which can stretch and spread in phase space, but it remains a Gaussian. So it's very crude, but it's better than the global harmonic approaches. And it's also expensive, but it's much more efficient because it just uses one trajectory. Okay. So what is this thawed Gaussian approximation? You assume that the wave packet has a Gaussian form, so it has a Gaussian envelope, but in addition, it is a complex Gaussian, so you see some oscillations. And finally, as of course, the oscillations can move with the phase velocity, which is different than the envelope velocity. All right. So the Gaussian can stretch and rotate in phase space, but it remains a Gaussian. And it has only 4 parameters: position, QT, momentum, PT of the center of the Gaussian, then the width matrix, and then finally the phase. And what is interesting, that the only approximation you need to make in order to justify this ansatz is so-called local harmonic approximation of the potential. So I will explain that in a moment. So it's definitely exact in harmonic potentials, but of course it doesn't describe wave packet splitting or tunneling. So it's very simple and crude. It was invented by Eric Heller already over 40 years ago. But it was originally used only for simple model potentials. And I will show you it's quite easy to apply to 100-dimensional system with ab initio electronic structure. So what is this local harmonic approximation? You basically replace the exact potential by a locally quadratic approximation. So you need the energy, gradient, and the Hessian of the potential at the center of the wave packet. So let me compare it with what people usually use to predict or analyze spectra. It's these global harmonic approximations. So instead of taking the exact potential energy surface, use a harmonic approximation. And it can be expanded either at the position of the excitation or at the minimum of the excited surface. So this is what we are trying to improve on. And the local harmonic approximation actually gives you a time-dependent effective potential, which has not only the exact energy and force, but even the curvature, and it moves with the wave packet. Okay, so it is very simple, but it is more accurate than these global constant harmonic potentials. But the time dependence will come back to haunt us a little bit later. It's not so bad, but it's also a small problem. So the simple derivation is that you use this Gaussian ansatz, you assume the local harmonic approximation for the potential, and that's all you need to do. If you substitute this into the Schrödinger equation, the result is exact for this effective potential. It's exactly equivalent to the system of ordinary differential equations for the parameters. So the position and momentum of the wave packet satisfies the Hamilton's equations of motion, classical trajectory, and in addition, you have two equations for the width matrix and for the phase of the wave packet. So this gamma parameter. And as you could have guessed, it is connected to classical action because it is an integral of the Lagrangian, but in addition, it has also a term which guarantees the normalization of the wave packet. Okay, so instead of solving the Schrödinger equation directly, we solve the system of differential equations. And now let me make a quick review how to compute spectra with this approximation. So far, it was just the solution of the Schrödinger equation, but now let's see how we compute spectra. So standard textbook approach to describe spectra, electronic spectra of molecules, is that when you shine light on a molecule, it will absorb in different discrete vibrational levels of the excited states. So the spectrum will have peaks at discrete energies corresponding to the excitation energies, and the intensities will be the matrix element of the transition dipole moment. What is, I think, much more beautiful picture is the time-dependent approach, in which you take the wave packet to the excited surface, let it evolve there, and then you compute the spectrum as a Fourier transform of the wave packet autocorrelation function. So you don't need to even compute the energy levels in the excited state. You just let it evolve. You can use approximate methods, and you can compute low-resolution spectra very quickly and easily. So let me give a few more details of this approach. The two crucial approximations are Born-Oppenheimer approximation and time-dependent perturbation theory. The Born-Oppenheimer means that we ignore non-adiabatic couplings between these two surfaces. So after the excitation, the wave packet stays there. The time-dependent perturbation theory means that the electromagnetic field is weak in some sense, but it is quite good in most of situations, of course, not always. The two remaining approximations actually can be relaxed. I will show you this at the end of or in the later part of the talk, but this is also what most people use. So first is a Condom approximation, where you assume that the transition dipole is independent of the nuclear coordinates. And the second one is the low temperature approximation, in which you assume that the state of the system doesn't have to be described by the density operator, but just by a wave function. And the reason is that the electronic excitation energies are so large compared to the temperature that you can think that you have a zero temperature. But this is an approximation, and I will also show you how to relax it. Okay, so as I mentioned, the spectrum can be computed as a Fourier transform of the wave packet autocorrelation function. And this is a standard picture, and everybody in chemical physics knows this. But what is quite interesting, again, since I know that many people in the audience are experts in the fidelity and Loschmidt-Echo, is that if you go back to the original derivation from perturbation theory, a much more fundamental expression is in terms of fidelity amplitude. So autocorrelation function is the overlap of the wave packet at time 0 with the wave packet at time t, and the wave packet is propagated in the excited state. Much more general expression is that you propagate the wave packet both in the excited and in the ground state and compute the fidelity. And the only reason why you don't need to always use this, because typically molecules are in the vibrational ground state, which is an eigenstate, so the propagation is trivial. It just picks up a phase factor, which shifts the spectrum. But if you look at more sophisticated spectra, you really need to think about the fidelity amplitude. So again, we are not trying to make very, very accurate spectra calculations, but we want to improve upon something, and we are trying to improve over these global harmonic pictures. So vertical harmonic is that you expand the potential in the region of the excitation, and the adiabatic harmonic that you expand the potential at the minimum of the excited state. And before I compare with experiment, in order to avoid errors of experiment and errors of the potential energy surfaces, let's look at a simple model Morse potential. So this is exact quantum spectrum of a Morse potential. And if you use the vertical harmonic approach, you might get very wrong frequencies, very peak spacing. If you use the adiabatic harmonic approach, you actually might be able to get pretty good peak spacing, but wrong amplitudes. And if you use the thawed Gaussian approximation, you don't get a perfect spectrum, but it is much better than either of the globally harmonic models. Okay, so this is exactly the motivation. It's very simple, but it can give you something more than the standard approach. And here I want to show something already realistic. So this is a spectrum of ammonia, and it is a small molecule, only 4 atoms, but what you see on the right is actually full 12-dimensional nuclear wave function. So this is not, these are not electronic orbitals. Maybe you've seen movies with electronic orbitals, but this is really, we had to write our own code to visualize the nuclear wave function. So it's 12-dimensional nuclear wave function. And although it is a small molecule, it's a complicated problem because the ground state doesn't look anything like harmonic. It's a double well. And the excited state also is not at all harmonic. So we didn't expect the simple method to work because it's so floppy. But actually it works pretty well. So here I compare the experimental spectrum with 2 calculations based on density functional theory, which is the blue line, and more sophisticated CASPT2 electronic structure, which is the red curve. If you use the thawed Gaussian approximation, both of them give you reasonable spectra, but I guess the better electronic structure gives a little bit better spectrum. It's not perfect, but there are so many things involved that we were quite happy about that. If you use the vertical harmonic approach, you get wrong peak spacing. And if you use the adiabatic harmonic, you get even artificial peaks, which are unphysical. And also it's very sensitive to the electronic structure. So anyway, so this was somewhat tough test, and we were very happy that it worked there. So now let's look at another example. So we can compute photoelectron spectra, we can compute fluorescence spectra, we can compute Raman spectra. Let me just show an example of fluorescence, which is emission. So now the situation is just inverted. You start in the excited state, and the molecule emits light and moves to the ground state. The calculation is pretty much the same, except that if you remember with the Einstein A and B coefficients from basic quantum mechanics courses, that now the spectra are proportional to the 3rd power of the frequency. Otherwise, it's exactly the same. And in fact, this was our first calculation with thawed Gaussians, and it persuaded us that you can apply them in quite large dimensions. So first, this is a molecule beta-iophene, which has already many more atoms than ammonia. And you see that if you use the standard harmonic approach, you get completely wrong spectrum. But if you use the thawed Gaussian approximation, you can capture almost all the peaks quite well. Not perfectly, but pretty well. And this, you can push it to, the oligodiophene with 5 rings, which has 105-dimensional wave function, which is again shown here. This is the nuclear wave packet in 105 dimensions. And you capture the spectrum again pretty well. It's slightly shifted, but this can be expected from electronic structure method errors. So, anyway, so this was the promise that we can do both semi-classical nuclear dynamics and at the same time very accurate electronic structure calculations. What is nice about semi-classics, because you have the trajectory, you have a lot of information which you can use to analyze the spectra. In fact, let me go back to this. When Marius showed me the calculations, which took a couple of years to put everything together. In the end, the calculations were shorter, of course, but to set this up, he was so proud that he got such a nice match with the experiment. And I was also very proud, of course, but I didn't tell him at first. I said, well, so what? You have a very simple spectrum. So what is so complicated about this? You have 105 dimensions and suddenly you have 4 peaks. Why is it so simple? And then I didn't hear from him for about 3 months. And when I heard from him back again, then he showed me a very nice way how to analyze spectra. And again, I know that a lot of you are experts in group theory and symmetry. So of course you can simplify spectra by group theory and symmetry. But sometimes when the molecules are not symmetric, it's more difficult. And here we had a 105-dimensional system. In principle, all the modes were coupled. So how do you interpret the spectrum? How do you determine which modes are the most important? And Marius developed a method based on partial decoupling of the modes and finding the most important modes based on the stability matrix. I will not show you the details, but just to show you that this is kind of a black box way to determine that the whole spectrum is pretty much determined by 8 modes, which are shown here. And if you are not interested in the broadening, but just positions of the main peaks, you can go down to 4 modes. So a lot of people confuse large systems with complex systems. And in some sense, the complex systems don't have to be large, and at the same time, large systems don't have to be complex. So here you can describe the spectrum pretty much with 8 normal modes. And this would be very difficult to extract from exact quantum calculations, even if it were possible, which I doubt in 105 dimensions. So I am not going to talk much about the technical details, but I want to show you that also we think about how we perform the calculations a little bit. So just one quick slide about the ab initio implementation. The thawed Gaussian approximation is very nicely done in normal mode coordinates. And so you have to find the normal modes in some reference geometry. So this is done usually that you mass scale the Cartesian coordinates, you find orthogonal transformation which diagonalize this Hessian. And when you run the calculation, on the other hand, it is done in Cartesian coordinates. When I showed you the movies, I showed you a movie of molecule where each atom had its Cartesian coordinates projected on the screen. So what you need to do is to transform to the normal coordinates, which is easy for translations. You just shift to the center of mass system. For rotations, you cannot do it exactly, but you can separate rotations and vibrations. Ideally, for example, by moving into so-called Eckert frame. And then finally, you transform the coordinates, you transform the gradient, which gives you the force on the atoms. And finally, you transform the Hessians, which you need to propagate the width matrix of the Gaussian. So that's the ab initio recipe in the nutshell. But I think what I find even more interesting is using the geometric integrators. So this allows us to conserve certain invariants of the exact solution exactly numerically. So even if your wave function has error, let's say 1%, you can conserve some invariance of classical and quantum mechanics to machine precision. And this can be done by splitting the Hamiltonian into the kinetic propagation and the potential propagation. So you can solve these 2 steps completely analytically. So it's trivial for position and momentum, which gives you, for example, the Berle algorithm of classical or symplectic algorithm for classical dynamics. But you can also do it for the width matrix. And you can do it also for the phase parameter gamma. Okay, so this is analytical solution, and you can compose them to obtain very efficient high order integrators, which I will show in a moment. But the more interesting thing is that you can conserve certain invariants of classical and quantum mechanics. So as you probably remember from classical mechanics, there is so-called Liouville theorem, which guarantees you conservation of phase space volume. And this happens also with our numerical integrators. You can measure it by the determinant of so-called stability matrix. And this determinant should be 1. And it is 1 to machine precision. As you see, the deviation is at the level of 10 to minus 14. But Liouville theorem is not the only conserved invariant in classical mechanics. So in more advanced classical mechanics textbooks, you can hear about sympathetic structure. And I joke about is that it implies million Liouville theorems. So if you have a system with million degrees of freedom, you will have million invariants which are generalizations of the phase space volume. And again, it depends on the stability matrix, and J is so-called standard symplectic matrix. So classical mechanics satisfies exactly this equation, but in our numerics, the equation is also satisfied to machine precision. Again, it is 10 to minus 12. There is some small drift due to round-off errors, but this is really negligible. And then finally, because we are doing semi-classics, so we have both some classical quantities and the wave function. And the wave function should conserve its norm, and it does, again, because we are using geometric integrators. So you see that the norm deviation from value 1 is again at the level of 10 to minus 15. So it's very simple. The code is very simple, but it guarantees you that. And then what is also nice is that you can speed up the calculations by composing these simple elementary potential and kinetic steps, and you can get integrators which can be second order, fourth order, sixth order, eighth order, 10th order, or arbitrary order in the time step. So this means that you can use much larger time steps and still converge to machine accuracy, which you have here at about 10 to minus 14. Whereas a standard code for classical mechanics only use the second order Verlet algorithm. So you would need to use much smaller time steps to obtain the same accuracy. Here I show as an example the convergence of the width matrix only, but we have the same convergence for position, momentum, and the wave function itself. Okay. So enough for the technical things. So now let me mention a couple of excited recent developments. And so first of all, what happens if the Condom approximation doesn't hold? This means that the transition dipole moment can be even 0 at the position of the wave packet. So now the wave function which moves in the excited state is nothing like a Gaussian. So we cannot use at all the Gaussian approach which I discussed until now. Okay. So an extreme example is the electronically forbidden spectrum of benzene. So as I said, the wave packet is far from Gaussian. It's more complicated. Here you can see the snapshot of the movie, but most importantly, if you use the method which I described until now, you would get this Franck-Condon spectrum, which is basically 0. There is no spectrum at all. That's why it's called electronically forbidden. However, it is vibrationally allowed because the transition dipole moment is not 0. It just depends on the coordinates. It's only 0 at the minimum. And so the experimental spectrum has the gray peaks, and you can see with the semi-classical approach, which I will describe in a second, you can get the main peaks quite well. These are the red peaks. Okay, you cannot get everything, the small peaks here, but those I will also discuss in a moment. So how do you do this? So if your transition dipole moment is not a constant, the leading approximation is a linear function of coordinate. This is so-called Herzberg-Teller approximation. Okay, so now the wave packet is a Gaussian times a polynomial, linear polynomial. It can again breathe while it moves. You know, it's one-dimensional movie, but we can do it in arbitrary dimensions. And what is exciting is that if you use the local harmonic approximation for the potential, it retains this form at all times. Okay, so it will be a linear polynomial times a Gaussian. And moreover, the only new parameter is this prefactor of the linear term, and this can be computed pretty much for free. So the marginal cost is negligible. Okay, so we can compute this at the same cost as thawed Gaussian approximation. And one thing which is interesting when you want to compare with experiment, you know that the molecules don't have to be aligned with the field. They can be randomly oriented with respect to the field. And if you have the Condom approximation, there is a standard textbook recipe. You just align the molecule with the field, you compute the spectrum, and then you divide it by a factor of 3. The question is, can you do this if your transition dipole moment depends on position? Can you just replace the transition dipole moment with its magnitude? Absolutely not. You would get completely garbage result. So now it seems like you might have to average numerically, but it would be a nightmare, right? Because each trajectory is very expensive. So if we had to average over orientations numerically, it would be very difficult. But it's beautiful fact of symmetry, we don't have to. It's quite easy to show that all you need to do is take arbitrary 3 orthogonal orientations, compute the spectra for each orientation, and make a simple arithmetic average. So that's all you need to do. And what is exciting for the ab initio applications, that the marginal cost is actually not 3 times more expensive, but it's 0 extra cost. So the reason is that you can use the same trajectory, ab initio trajectory, you only need to do some analytical calculations to compute the spectra with the different orientations. So this you have to worry if you want to compare with experiment. This is the quantum nuclear movie in, I don't know, I think it's maybe 30 dimensions now. So it's not huge, but it's much bigger than the ammonia. And now the red and blue lobes tell you the positive and negative part of the wave packet. Okay, so the motion is quite simple, but it is really the 30-dimensional wave function. And now let's see how it works. So again, it is nice that we can improve over standard approaches. If you use the vertical harmonic approach, you get artificial peaks. If you use the adiabatic harmonic approach, you get the correct peaks, but wrong amplitudes. And if you use the thawed Gaussian approximation, you don't get the perfect spectrum, but the amplitudes are within 5%. And these things which we cannot describe are due to finite temperature. But I will show it to you in a moment that we can actually get them too. But this was even more recent development. And then once more, I want to remind you, if you just use a Gaussian wave packet, you would get no spectrum at all because it's electronically forbidden. So the only reason we can get the peaks is because we propagate more complicated wave function than just the Gaussian. All right. So how can we accelerate the calculation? It's whatever I discussed until now required computing a Hessian of the potential energy at each step. And even for somebody who doesn't worry so much about electronic structure method, imagine that you have a function of 100 coordinates. How much more difficult is to compute the gradient? If you do it by finite difference, it would be 100 times more expensive. If you want Hessian, it would be 10,000 times more expensive, right? So you want to avoid computing Hessians. And with that, for that, Tomislav Begusic came up with a neat approximation, which we call single-Hessian approximation. Excuse me. So it's very similar to the local harmonic approximation, that your potential is time-dependent, but now you keep the curvature constant. So you have the locally exact energy and gradient, but the Hessian is kept constant. And again, you have two options. The vertical Hessian uses the curvature at the excitation point, and the adiabatic Hessian uses the curvature at the minimum of the excited surface. So now you just need to compute one Hessian. And at first, it was just a pragmatic way to speed up calculations. But we found, in a moment, I will show you that it has some deeper consequences. So it's electronic structure people talk about the hierarchy of density function of and they compare it to Jacob's ladder in the Bible. So here we have a quantum dynamics, Jacob's ladder. In the heaven, you would have the exact quantum calculation, and at the bottom, you would have the global harmonic approximation. In fact, there are much worse approximations than that, because this one at least takes into account so-called Tuscinski rotation and mode distortion. But anyway, and for us, we are not so ambitious, so our ideal is the thawed Gaussian approximation. So you can imagine you just interpolate the Hessians along the trajectory, you don't compute it at each step. So this we did first. But we found that sometimes the single Hessian can give you a better result than if you interpolate every 16 steps, for example. So it's a little bit surprising. But now this one is quite exciting, because if you have just one Hessian, it's pretty much similar cost to the global harmonic approximation, which also needs just one Hessian. Here you just need, in addition, the trajectory, but the trajectory is usually much less expensive. So let's see how it works in ammonia. So first of all, we didn't expect this to be better than thawed Gaussian approximation, but in ammonia, it seems to be even slightly better. So this was the thawed Gaussian result, and you see that it's quite good, but the minima between the peaks are not perfectly described. With the single Hessian, there is a little bit of an improvement. So this was, I think, just a little bit by luck, but maybe not completely. Because you have time-dependent potential, you don't guarantee conservation of energy, so you might get small negative peaks, which are artificial here, right? In the single Hessian, you can still have small negative peaks, but they are much reduced. It's hard to see over here. And the adiabatic harmonic approach is definitely by far the worst. And it's not much less expensive than this middle panel. So this was quite interesting. And so we wanted to analyze much more what is so nice about this single Hessian version. And as I mentioned, because your potential is time dependent in the thawed Gaussian approximation, you don't expect conservation of energy. Well, it can be analyzed a little bit further. You can separate the classical energy of the center of the wave packet, which is conserved exactly because it feels the exact Hamiltonian, which is time independent. But the semiclassical contribution depends on the current position of the wave packet. So it is time dependent, and this one violates the conservation of energy. So you can see it here. The red line is the exactly conserved classical energy of the center, and the blue curve is the time-dependent energy, which is due to the finite width. You would expect the same thing for the single Hessian approximation, but there is a magical cancellation. So, and it turns out that the energy is exactly conserved. You can derive it simply by computing the expectation value of the time derivative of the potential energy in the single Hessian approximation. And it's a little bit like telescoping identity. You cancel first term with the second one, second with the third, and so on. And in the end, you get exactly zero. So you can see it here. The total energy in the thawed Gaussian, which is in blue, is not conserved, but the red and green lines are the single Hessian versions, which conserve the energy exactly. So this is one aspect in which it is actually cool. It's not just a pragmatic approximation to speed up the results. But there's one more thing. There's one more thing, which is also very geometric. So I told you how we propagate the width matrix, but there is another approach based on factorization of the width matrix into complex capital P and Q matrices, which satisfy equations very much like classical Hamilton's equations of motion, not with the original Hamiltonian, but with the linearized Hamiltonian. So you have a Hessian of the potential energy. And so you can derive them from a Hamiltonian, which is here at the bottom, which is unfortunately time dependent because it depends on the position of the wave packet. And that's why thawed Gaussian approximation doesn't conserve energy. But in the single Hessian approach, you can map the quantum problem with the original Hamiltonian to a classical problem in these higher dimensions with QP and capital Q and P. And the classical equations for small q, small p, and capital Q and capital P give you exactly the evolution of the quantum wave packet. And because the expectation value of energy is given by the value of this mapped Hamiltonian, this is an alternative proof of the conservation of energy by the single-Hessian approximation. So I found this fascinating, and it's closely related to the time-dependent variational principle, which maps the quantum problem, which is linear, to a nonlinear classical problem in the parameters, and it also always guarantees conservation of energy, no matter how bad your variational ansatz is. So, okay. And now let me mention the last, and I think for me most magical development, how we can describe finite temperature. So for electronic spectra, the finite temperature is often not the most important effect, because the electronic energy is much bigger compared to ambient temperature, but sometimes it can play a role. And we can do this with wave functions instead of density operators. So if you want to compute spectra at finite temperature, normally you would need to use density operator. And you would have to completely change your equations of motion. You need to solve not Schrödinger equation, but quantum von Neumann equation. It becomes much more expensive, so you can treat only few dimensions. So here we use a trick, how we convert the thermal dipole correlation function to a wave packet autocorrelation function, but in higher dimensions. And we map it to the original problem that we solved in what I discussed until now. So you can compute the spectrum as a Fourier transform of this dipole autocorrelation function, which depends on the density operator of the system. But you make a small trick, we'll factorize it, the square root of the density operator. You keep one here, you move one around the trace over here, and then you split, you represent the trace in position representation, and you will have two factors. One can be interpreted as a wave function in twice as many dimensions, and the second factor can be interpreted as a time-evolved wave function in higher dimensions. So altogether, you get again a wave packet autocorrelation function, except now you have d original degrees of freedom and d fictitious degrees of freedom. And your Hamiltonian is the difference of one of the Hamiltonian in the original degrees of freedom and the ground state Hamiltonian in the fictitious degrees of freedom. So it sounds a little bit magical, but this is really most of the trick. It's very closely related to so-called thermofield dynamics, which has been used in quantum field theory to describe finite temperature effects. But I think this is a much simpler case. Okay, so the only issue is that we double the number of degrees of freedom. But if we can treat 100 degrees of freedom, we can treat 200 degrees of freedom. Whereas in quantum mechanics, if you can treat 10, you probably cannot treat 20. Right? With semiclassics, you can afford it. And what is also interesting, that for the ab initio electronic structure, we are still having to deal with only with 100 degrees of freedom. So again, the marginal cost is zero. So, and what is also nice that we don't need to program any new equations of motion. We just need to map it to the zero temperature problem. So when we solve the zero temperature problem, we need to set the initial position, width matrix, and phase. Now we do the same thing for the twice as many dimensions. The only thing which is a little bit more complicated is the width matrix, which takes into account the finite temperature effect. But otherwise, it's very simple. And the potential energy is again local harmonic approximation, but it's applied to the difference of the two potential energies, one in the original and one in the fictitious degrees of freedom. So I'm not going to dwell on this, but let me show you that you can also visualize it in an interesting way. So the most trivial example is a one-dimensional harmonic potential. This is your original degree of freedom. This is the fictitious one. At zero temperature, there is no correlation between Q and Q prime. At the high temperature, there is a correlation already in the initial state. When you start to propagate, at zero temperature, you just oscillate in the original degrees of freedom, and nothing happens in the other ones. But at high temperature, the correlation evolves. So there is not only this vibration, but also some rotation. Okay. And so let's see how it works. So this is, I showed you before, the zero temperature calculation of the benzene spectrum. And you see that it was we could not capture these additional peaks, which are so-called hot bands, which are exactly due to the finite temperature. But with this extended thawed Gaussian approximation at finite temperature, we can capture even these hot bands. And we were very excited about it. It's not perfect, but you cannot expect it because there are so many difficulties with the electronic structure methods that we were very excited about that. And I think I'm running out of time. So I just want to advertise one last thing. So whatever I discussed until now would be quite simple experimentally. Not everything, but it's relatively simple experimentally. For the theory, it was very difficult to combine everything together. But now what is cutting edge in the experiment are time-resolved electronic spectra and two-dimensional spectra. So the experiment goes from, I don't know, $1,000 to $1 million equipment. And but for us, it's not so much more complicated. We just need to, it's a little bit more expensive, but you deal with more complicated correlation functions, especially when you deal with fidelity, but otherwise, in some sense, we are ahead of the experiment because we can obtain more vibrational resolved spectra. Here is an example of a spectrum resolved as a function of frequency and time. So how does it work? So again, you can compute the spectrum as a Fourier transform of some correlation function, which is, in this case, a fidelity amplitude. Again, I mention it because people in Cuernavaca have dealt with this a lot. So the correlation function is a more complicated sequence of propagations. So first you propagate for a delay time tau in the excited state. Then the probe pulse sends the wave packet back to the ground state. And then after that, you propagate it both in the excited and ground state for time t. So in some sense, you can think of it as a fidelity with a non-stationary initial state, which is obtained by propagating for a delay time on the excited state. So it's really simply fidelity amplitude. And so in this simple picture, we assume non-overlapping pump and probe pulses. And what is nice in theory compared to experiment, that you can separate different contributions. So here is, for example, the time-resolved stimulated emission contribution. And I want to say that these strange wiggles are not due to some numerical artifacts. These are the vibrational resolution of the spectra. Okay. In experiment, you cannot separate so-called ground state beach, which is mixed with the time-resolved stimulated emission signal, but we can easily compute the two and combine them together. So if you wanted to compare with experiment, this would be what you would compare. And you can see these oscillations are due to the changing energy gap between the ground and excited state. So you also see the wave packet oscillations with the frequency of about 36 femtoseconds. So you can learn a lot from these calculations. And the last thing, which is really just an advertisement in a paper published about a month ago, that we can also compute two-dimensional spectra, which are even slightly more fancy correlation functions, based on slightly more fancy correlation functions. So we can do it also ab initio, but here I just show a comparison in a model potential where I compare exact calculation with thawed Gaussian approximation and the harmonic calculations. Of course, it's a little bit hard to see the errors in these two-dimensional pictures. It's better to look at the slide, but these points B and C already show you that there are certainly the harmonic approach is worse than the thawed Gaussian. Okay, and so with that, I think I told you enough. I hope I didn't completely saturate you. So I would like to conclude. So I hope I persuaded you that ab initio semiclassical dynamics as an interesting way to combine quantum nuclear dynamics approximately with accurate electronic structure. So you treat quantum mechanically both electrons and nuclei. And even the simplest thawed Gaussian approximation can give you an interesting, quite accurate results for vibrational resolved electronic spectra. Certainly better than what you get from some standard packages which compute the spectra for you. And then I mentioned a few extensions. One of them was how to compute electronically forbidden spectra, where you needed to propagate something more than a Gaussian. How to accelerate it with the single-Hessian approximation, which also conserves the energy exactly, and how to compute spectra at finite temperature at zero additional cost without using the density operator. And then finally, I only advertised that we can also compute time-resolved and two-dimensional spectra, but I didn't discuss it much in detail. So once more, I would like to thank all the people who contributed to this, especially Tomislav and Marius, but also Rhea, Solen, Organian, Julian, and Miroslav. And I would like to thank different sources of funding. And most importantly, thank you for your attention. I know it's not so easy to listen to talks over online compared to in live, where it's much easier to interrupt all and ask all the time. But I hope you have some questions, and I'll be happy to answer them now. So thank you.
Thank you very much, Jiri. Thank you very much for this very, very beautiful talk. And yeah, are there questions? Antonio, you have a question?
Yes. First of all, thank the speaker. It's really impressive what you can reach with this ab initio semiclassical dynamics, and it was a very nice talk. So thank you. And my first question is, you are within the Born-Oppenheimer approximation, I'm guessing, right?
Yes.
In all of this, I was wondering if you could treat with this nice thawed Gaussian approximation some more perhaps challenging problems, such as ironic coupling, you know, which couple the electronic vibrational rotational modes and may be relevant in, say, radiationless transitions. Would that be possible, or that's a stretch? Okay.
So interesting, very good question. So in fact, the movie which I showed you in the very beginning, the movies, they were non-adiabatic. That the wave packet was moving from ground to excited state, and also the trajectories were switching that. But it's true, I didn't use it with the thawed Gaussian approximation. That was a different method. I have a, you know, we of course thought about it a lot, what you asked, and we are now. So we are planning, so you can generalize that use more Gaussians. You can propagate several Gaussians in each electronic state. And in fact, there are other groups who are already involved in this. For example, Todd Martinez in Stanford and Dimitri Shalashilin in the United Kingdom. But what I was thinking, these are kind of a little bit brute force calculations that you have basis set and run many Gaussians, so it becomes quite expensive. What we were thinking about using a Gaussian which moves with the mean field approximation over like a generalization of Ehrenfeld dynamics, and sure. But this would work in systems where you have hundreds of electronic states. So really, mean field makes sense. If you have only 2 or 3, it would give you a garbage result.
Sure, right? Sure.
So but it might be interesting for systems which you cannot solve in any other way. And then,
absolutely.
And then, but it's true that what you were mentioning, that, for example, we could use this method for computing radiationless transition rate. So we were thinking about it a long time ago, but until we could do the finite temperature calculation, it didn't make much sense because you compare one number to one number, and there are so many things that can go wrong that it's kind of meaningless. But since now we have the finite temperature approach, we can look at the radiation. So what is it? This Fermi golden rule transition rate as a function of temperature. And so I think now it would be interesting. So we are thinking about going back to that. But again, it's treating non-adiabatic dynamics within perturbation theory. Right? So
yeah, okay.
Thank you also for the suggestion. Yeah.
Well, thank you.
Are there further questions? Comments?
Well, I would like to thank Jiri very much for a talk that showed impressive progress in a number of directions. There was something that puzzled me. The two-dimensional spectrum, you said that it was obvious if one looked at points A and B that the newest approximation was much better. Now, the first thing that surprised me is that the harmonic approximation is as good as it is. But maybe you could tell us why these points are so different. I'm not really able to see it.
Yeah, so it's it's my Tomislav put it there. You know, it's also hard to see at first sight. I think if I could go to the paper where there is a slice, you could see it maybe a little bit more. So I think there is I think it becomes more blurred here, that you don't have so much the vibrational resolution as in the, if you go, let's say, beyond 0.4, I don't see, there are not so much vertical lines, right? It's just horizontal lines, not so much vertical, whereas here you have also vertical. It's very weak, it's very weak. But I think I can address slightly your comment why the harmonic approximation is so good. So this was also a little bit frustrating for us. For the simple spectra, the harmonic approximation was usually very bad, but for the time result spectra, it was sometimes not as bad as you might expect. But I think we understand it. So I think I even have it in my talk somewhere at the, it's the last slide in the appendix. So this is really, there is a cancellation of errors. And you can see it. You see, this is an example, let's say, with two Morse potentials. And if you make a harmonic approximation both in the ground and excited state, you make an error in both states, but they partially cancel. Whereas if you have a simple, and for time resolved spectra, you need to propagate really with fidelity with both potentials. Whereas if you do the calculation, for example, just for absorption spectrum, then you approximate only the excited state, and there is no propagation in the ground state. So there is not as much cancellation of the error. So it's a little bit frustrating, but yeah. But
I mean, I'm sure that there must be other examples where the difference will be bigger. But okay, now at least I see what is the point. So to say, in the very small amplitude range, it's different. It may be I mean, if you look at the percentage error, it may be quite big.
Yeah. And here in the movie above, you see that the global harmonic gives you different results and then on the fly calculation, but it's not so huge. And but what is it? So we computed even on the fly two-dimensional spectrum of phenol, and there the global harmonic approach was almost perfectly agreed with the thawed Gaussian approximation. So again, this was a little bit frustrating, but what was nice that most people don't even use the global harmonic approximation, because that one is already quite complicated. It takes into account that the normal modes in the excited state are different than in the ground state. So most people, what they do, they just take displaced harmonic oscillator, like let's say 100-dimensional displaced harmonic oscillator. They take a paraboloid in the ground state and in the excited state displace it to make a model of the potentials. And that gave a completely wrong result. So we could at least improve on that, but yeah, sometimes the harmonic is not as bad as it can be, but sometimes it is.
If we just use the Gaussian, the program Gaussian and its extension for vibration after having done the calculation, which is a harmonic approximation, and I think it's a global one. Is that what you refer to, the global one? Or,
yes,
or an example for the global one?
Yes, exactly. So it is done in the Gaussian. They use the global harmonic approximation. But again, to be fair, people have included perturbation theory, vibrational perturbation theory corrections to the global harmonic model. So I'm not sure in which Gaussian it is included and exactly in what combinations. I think my students would know more precisely. So like in the standard textbook, in one dimension or even quantum field theory, you always learn harmonic oscillator and then you include third order and fourth order by perturbation theory. So that's what they did, and that gives a significant improvement. Okay, so I think it doesn't always have to be as bad as a harmonic, but it's the basic calculation in Gaussian is harmonic, unless you include the perturbation theory corrections. So you have to specify it.
Jenny, do you have an idea if in the paper we made on the vibration, whether such corrections were included?
Okay, maybe we
She's there. She just opened her mic. Hi,
okay.
Jenny. Hello, Jenny. We can't hear you. Well, it seems it doesn't work. Anyway, I'll...
¿Me oye?
Yes.
Ahora sí.
We
Yes.
hear you.
Hello.
Sorry.
So I just wondered, in these vibrations we show, like the film in the paper, I think it's in chemical physics letters, how are the vibrations treated?
I can't hear.
As far as I know, global harmonic approximation. As far as I know.
Do you hear me? Hello?
Yes,
we hear you.
Okay, now I can hear you. What was the question?
The approximation we use in the vibration paper, I think it's in chemical physics letters.
Yes.
You know which one that is?
The calculations are made in global.
Are made in global. Okay.
With But we didn't include the corrections, actually.
We did include corrections. Okay.
So it is kind of interesting because so it could be sometimes even better with the correction, with the perturbation theory, it could be better than the thawed Gaussian. So we include the exact trajectory, so the fully anharmonic potential, but semi-classically, whereas the global harmonic with perturbative treatment of third and fourth order corrections, by the way, which of course becomes very expensive because how many fourth order terms there are in 100 dimensions? There are many. So that doesn't take into account the full trajectory, but at the same time, it includes perturbatively, quantum mechanically, maybe more.
But I think we should discuss that maybe once in private, Jiri.
Sure.
I'll send you the link and then we can discuss it. Maybe together with Jenny. Thomas, I think he's also in the paper or not, I don't remember.
Yes, that will be good.
Okay, there is a related question from YouTube. Rodrigo Cid Molina is asking, can you explain with a bit more detail what the global harmonic models are? I don't know, you said already something really.
No, but it's good to say it more precisely because I was maybe very quick. And also it's very important because I always show one-dimensional picture, although the calculations are in many dimensions. So in one dimension, you cannot see everything. So where was it? Okay, here is the global harmonic. So this is just one-dimensional picture. Global harmonic means that the harmonic potential is constant, it's fixed, it's just a harmonic. So instead of treating the full, blue curve, you just have the green one or the red one. It's a problem. But they're not as simplistic as it is shown here in one dimension. So in higher dimensions, you have several effects. because even if you have two harmonic potentials, which are maybe, let's say, 10-dimensional, there are two effects. You can change force constant between the ground and excited state, and then you can also rotate the normal modes. The normal modes don't have to be aligned between the ground and excited state. So when I say global harmonic model, this is the most sophisticated harmonic approximation that you can make. Many people use cruder approximation. First, they assume that the normal modes are the same in the ground and excited state, but at least include the change in the force constant between the ground and excited state. And then the second one is that they just take the ground state harmonic approximation and then shift it in the excited state and keep the same force constant and the same normal modes. The only difference is the displacement. So these are called displaced harmonic models. And then the effect that the normal modes are different in the ground and excited state is called Duschinsky rotation. So when I mention global harmonic, includes the mode distortion and also the Duschinsky rotation. So this is the best global harmonic thing that you can do. And I think that Gaussian does it normally, but you can probably make the simpler versions as well.
Okay, thank you, Jiri, for this explanation of the global harmonic model. I have a related question to your ab initio calculations. So how do you calculate, let's say, VE, the excited energy potential landscape? Because, well, DFT is made actually for ground state calculations. So how do you calculate the energy landscape, or how do you make afterwards this local harmonic approximation to it?
So exactly. So if we use density functional theory, then for the excited states, we use the TD-DFT, time-dependent density functional theory. So that you can do. And but when we use wave function methods, then if you use CASPT2, this is a complete active space second order perturbation theory, that takes care of both ground and excited states. So it depends. It actually depends on the system. Sometimes density functional theory is okay, and that's we most of the time use density functional theory, but for the ammonia we could use a more sophisticated method. Then when we use in some calculation we use complete active space self-consistent field CAS-SCF, which is cheaper than CASPT2, but it's also takes care of several systems. Then sometimes we use equations of motion, coupled clusters, which can also state average equations of motion coupled clusters that can also take into account some excited states. But mostly it is density functional theory and time-dependent density functional theory with the same functional in the ground and excited state.
Okay, I see. Do I understand that this is the only input parameter of approximation which you have, right? Which the DFT functional or basis which you use to describe the molecule?
Well, that's the approximation that's the first approximation, and the second one is the local harmonic approximation. So we don't compute so
okay.
Electronic structure, of course, I think. So if we had the exact potential energy surface from density functional theory, it would be crazy to compute it in 100 dimensions. But on the other hand, the errors might be actually bigger there, right? So the electronic structure, you're correct that it's the choice of the density functional, then it's the choice of the basis set, which is used to represent it. And maybe I should mention, that the errors in the electronic structure are so huge that it can be 1 electron volt, whereas here we have a quite resolved spectrum. So we shift the spectrum so that the highest peak corresponds to the highest peak from the electronic structure. We didn't do it always. In some cases we left it alone, but I think this is fair. So usually the electronic structure has a huge absolute error, but it has a hopefully, not so bad relative errors. But still, I think some of the errors in the peaks are more due to electronic structure than the thawed Gaussian approximation, no matter how primitive the thawed Gaussian approximation is. Yeah. So it's kind of preparing for the future. The electronic structure will always be the bottleneck in terms of accuracy and efficiency.
Well, you have a very impressive agreement of these peaks, which you calculate to experimental data. So
it's a little bit surprising, but these are quite simple spectra, low resolution. Right? It's when people talk about vibrational spectroscopy or raw vibrational, they have much higher resolutions, which would require long dynamics. And there, the thawed Gaussian approximation would completely fail. As we know, people from quantum chaos, right? You can a Gaussian localized wave packet makes no sense after Ehrenfest time and so on. So here it is actually it assumes some simplicity of molecules. That's it.
Okay. So maybe one last question for me. Could you comment on how much faster is the local harmonic approximation compared to these exact solutions which you showed for very simple systems? So how many order of magnitudes do you gain?
No, so this is a hard question to answer, right? Because we can do the local harmonic in 100 dimensions ab initio, but the exact one we can do in 4 dimensions. And so most things which I showed exact calculation were even 1-dimensional. Okay. So I think it was comparable. I would not be even surprised if the semi-classical calculation were slower, but probably it was not. Probably it was not, because it's still more expensive to do exact quantum calculation. So this is hard to compare, unfortunately. So that was kind of the point. There is no way to compute the exact spectrum for most of the things which I was showing. And maybe for those who are not chemical physicists, so there is what people use now for exact quantum calculations in high dimensions, and they really try to push high dimensions. But by high they mean 20 or 30 degrees of freedom. So actually close to some of the things which I did. It's called multi-configuration time-dependent Hall-tree method, which is a time-dependent basis set solution, and it is numeric. If it's numerically converged, it's exact. The problem is that it requires a potential energy in the sum of product form. So you need to spend a lot of effort to design a nice potential so that you can apply it, and it's very difficult to set it up. After that, you might be able to do 20 or 30 dimensions, but it's extremely difficult to set up the potential energy surface beforehand. Yeah. So these are about the records that you can do exactly quantum mechanically. Yeah. But,
okay, I see. Okay, thank you very much, Jiri. Are there further questions, comments from the audience? Yeah, if this is not the case, I think we had already some few discussions. Thank you very much, Jiri, for this very beautiful talk. Yeah, it was a pleasure for me to have you here today. Yeah, we hope the next time in person to host you in Cuernavaca. And yeah, thank you very much, and see you next week.
Sounds good. So thank you very much for the invitation. Yeah, it was it's always nice to talk to you.
Bye bye, Jiri. Thank you very much.